Hi there. I'm Garrett Thomas. I'm from the Robot Learning Lab at UC Berkeley. I'm here to present our work, Learning Robotic Assembly from CAD, which was done in collaboration with Siemens. According to the International Federation of Robotics, there are an estimated 1.8 million operational industrial robots as of last year, and this number is still rapidly increasing. Simultaneously, there's a recent trend toward product customization, which means that assembly lines must be flexible in order to maintain profitability with small batch sizes. However, it is currently the case that control software for automation is rebuilt to some extent to handle product changes. We would like to reduce the amount of engineering effort that is required to produce controllers for robotic assembly tasks. In such tasks, we have known geometric information about the objects that we're manipulating in the form of CAD models, and we can use this information to formulate a motion plan that will help us solve the task. However, this motion plan, although it solves the task in a geometric sense, does not know about the dynamics that will be encountered when we attempt to execute this plan in practice. In addition, as a result of pose estimation error, the controller may encounter unanticipated contacts which impede it. So a bit of background on motion planning. The goal is to find a collision-free path from the start configuration to one or more goal configurations, which avoid the obstacles which we assume to be, we assume that we know the configurations which correspond to collisions in the environment and want to avoid these. A number of approaches have been proposed in the literature to perform motion planning. Some are based on potential fields. Others are based on sampling-based planners, such as the class of PRMs and RRTs, which sample configurations from the configuration space and attempt to connect them in a graph structure. There are also trajectory optimization-based approaches, such as CHOMP, which iteratively refine a guess at a trajectory until it is both feasible and performant according to some performance criteria, such as path length. So motion planning has been applied in a number of places in manipulation tasks before. So for example, you can incorporate constraints into the planning process to incorporate, for example, torque limits or plan along two-dimensional surfaces. Another line of work integrates the motion planner with a higher level task planner so that the task can be specified in some high level language and then planned all the way down to individual motions. It's also worth pointing out that motion planning has important applications. For example, in the medical field, the problem of accurately inserting a needle into a patient's arm has been approached with motion planning. However, our work considers a scenario which is different from these previous works in the sense that the task requires high precision and a good dynamics model is not available to us. So here we illustrate how pose estimation error can cause problems for control based on tracking a motion plan in this scenario. So we have to estimate the poses of certain objects in the environment, so the pose is the position and the orientation. And this process is imperfect. So the poses that we assume when planning are somewhat different from the actual poses of the objects in the real world. And we can see that even if we have a perfect tracking controller, we may encounter contacts as a result of this misalignment. So this is not just a hypothetical issue. We actually try this, and this happens. So here we estimate the positions of the objects in the world. We generate a motion plan that will solve this task, and then we run a standard tracking controller from the ROS PR2 libraries. And we can see that in both cases, as a result of this misalignment that was previously discussed, this tracking controller gets stuck from these contacts and is unable to complete the task. Okay, so what else can we do? Reinforcement learning is a powerful way to autonomously acquire control policies. However, for real-world tasks such as robots, it may have unacceptably high sample complexity. But what's worse is that RL methods are typically based on some kind of local search, and if your reward function is not sufficiently informative, it will converge to a local optimum that does not solve the task. So for example, in the diagram here, the task is to move the ring onto this peg. So because of low tolerance, random exploration is very unlikely to solve this task on its own. So if our cost function is to just minimize the distance from our current position to the goal position, we'll just run into a locally optimal policy which moves in this horizontal fashion, as shown in the red here, and does not learn how to move up and around in order to solve the task. So to combat this issue, some people engage in reward shaping, which means that you essentially can hand design a reward function which guides the learning process in order to solve this challenging task. But it turns out that reward function is pretty difficult, even for experts, as a result of unintended consequences. And what's worse is that it requires task-specific engineering. So even if you design a reward function for one task, once you have a new task, you have to start that process over again. So we want to reduce the amount of engineering effort that's required, so we don't want to do this. Here we illustrate what happens. So this is the issue previously described, whereby when you run reinforcement learning and on this somewhat naive cost function, which is just the distance to the goal, we can see that in both cases the policy gets stuck in a local optimum where it greedily moves towards this goal position but never explores enough to move up and around and solve the task. Okay, so what can we do? Our approach combines the complementary strengths of motion planning and reinforcement learning in the following way. The motion plan is used to define a cost function, and by minimizing this cost function, we will encourage the policy to follow the reference trajectory set forth by the motion plan. So this LT could be, for example, the Euclidean distance between the end effector positions at time t and the reference position at time t. So to minimize the cost function in our work, we're using a variant of iterative LQG, although in principle another algorithm could be used. So in this algorithm, for each trajectory, we're going to train a time-varying linear Gaussian policy, which is one that has this form. So after a local approximation to the dynamics and a quadratic approximation to the cost, it turns out that you can use dynamic programming to solve for a locally optimal set of parameters for this controller. Then, since we assume that we do not know the dynamics involved in this task, we're just going to estimate them from samples. So this is where the experience comes in. So we'll perform rollouts with this controller and then use these to estimate the dynamics for the next run, and then repeatedly, iteratively improve this controller. Now, a lot of the details about this are not particularly important for our purposes, but there is one that is. So because of this linear form of the controller, we can initialize it with a tracking controller of this form. So we pick these matrices K0 and C0, and then, so now we have this tracking controller is not good enough to solve the task, probably. If it were, we wouldn't need to learn anything, but it is much better than a completely random initialization, which is what you would have to do if you didn't have any prior knowledge of the task. And this leads to a reduction in sample complexity, which, if you recall, is one of the issues that plagued our algorithms as described earlier. So here's the whole system as described so far. We have these geometric information, these CAD models of the objects that we're assembling. We're going to estimate the poses of these objects in our environment. Then we assume that we have access to a goal state, which is a configuration of the robot arms, which corresponds to a successful insertion or completion of whatever task we're trying to do. We then use motion planning to generate a geometric plan that will solve this task. This induces a cost function, which is then minimized by a reinforcement learning algorithm. And we get a tracking controller for this motion plan. So here's this method in action. We can see it applied to 3 different fairly challenging assembly tasks. These are pretty low tolerance tasks on the order of a millimeter or less in each case. And you can see in particular that the controller is able to succeed in spite of contact and friction forces that it encounters along the way. I should mention that this middle task here with the gear comes from our collaborators at Siemens and is motivated by actual assembly tasks that they're interested in, and that the CAD models for this task have been made publicly available to facilitate future benchmarking of assembly algorithms. So here's a more quantitative comparison of these things. We have, again, 3 tasks. For each, there's an easy version and a hard version. So the hard version is essentially what you saw on the previous slide, where some kind of complicated motion, such as a twisting or maybe an up and around motion, is required to solve the task and would be pretty challenging to do without some kind of guiding motion plan. There's also an easy version of the task, which is more straightforward. For example, the peg being placed, initially placed directly above the hole in which it is to be inserted. And we can see that in all of these cases, our method is able to solve the task successfully, and the other methods struggle, except that pure LQG is able to solve the easy version of the peg insertion task. Okay, so that's all well and good if you just have a single initial position and a single goal position. But now if you have a new initial or goal position, you have to repeat this process over again, because these ILQG controllers are specific to one trajectory, right? So to alleviate this issue, we propose a neural network architecture which accepts the reference trajectory as an additional input and learns to track this input. So here, these Ds here, these are offsets from our current position to nearby positions on the reference trajectory. We take a window from t minus k to t plus k. We then employ a softmax-based attentional mechanism to select just one of these directions. And then this attended direction is fed as an additional input to the policy to select a control. So here we set up a sort of train test scenario in the supervised learning sense. So we have 10 IOQG policies which were trained to successfully solve the task. And then we use behavioral cloning to train the neural network controller to imitate these policies. Then we test it on 20 trajectories that is never seen before. And we can see that the generalization is pretty strong here. It actually performs as well on the test trajectories as it does on the training trajectories. So here's a visualization of the execution of this trajectory. You can see that this test trajectory, which is shown in green, this has never been seen before by the network. So we do have to generate a motion plan in order to feed into this policy, but the important thing is that we do not have to relearn the control policy for that trajectory. That information has been learned by the network. So in conclusion, our method is able to successfully combine the complementary strengths of motion planning and reinforcement learning to solve some challenging assembly tasks. So the motion plan provides us with a cost function, which is to be minimized by a reinforcement learning algorithm, such as IOQG. It also provides us with an initialization, which reduces the sample complexity of this learning process. To provide generalization over task modifications, we propose a neural network architecture which accepts the reference trajectory as an additional input and learns how to track this. Some future directions that we think would be interesting to explore include image observations for the neural network. So this provides a very rich extra source of information from which to learn. We could also integrate our approach with a larger assembly planning pipeline, for example, to provide the initial or goal configurations for the manipulation task. Okay, thanks for listening.
Okay, thank you. Let's see if we have any questions. So let me ask one. Mm-hmm. So is it clear what kind of task complexities you can handle? Right now you have sort of pack and hold, and you have sort of a geometric insertion, but is it clear how complex a set of tasks would it be able to generalize to?
How complex a set of tasks? That's a good question. So I suppose we don't have tasks for which our method failed. So that would be an interesting thing to find.
So, but my question is, did you try hard enough?
Did we try hard enough? I suppose some tasks that would be more complicated. So if the tolerances were even lower somehow, such that the contacts were in a sense inevitable, it would be difficult, if not impossible, for the purely geometric motion planner to find a plan that successfully solves the task, which would limit our method.
Okay. Okay. Thank you. There will be a diploma here.